So now that we've discussed some of the vascularization of the cardiovascular system, meaning our arteries, veins, arterioles, venules, and looking very briefly at our capillaries, I now want to explore looking at what their purpose is, which is to ensure blood flow and appropriate levels of blood pressure and peripheral resistance. So when we're looking at our blood flow, it essentially is just looking at the measurement of how much blood is able to move around a system at any one time. Now we actually do have the ability to calculate this, and how we do it is to look at blood pressure and peripheral resistance, because blood pressure enables blood flow. If there's no pressure, there's going to be no flow. However, if we have too much peripheral resistance, this is like an opposing force that is holding back our blood. So think of it like when you're walking along the floor. If you're dragging your feet, it's sort of a degree of friction. It makes it harder for you to walk forward. That's what we're seeing here with our peripheral resistance. And we are able to calculate it using the following equation. And that is our blood flow is equal to delta P. So delta, the triangle, that is a Greek symbol that means a change in. So our blood flow is the change in blood pressure divided by peripheral resistance. Now, what this equation essentially tells you is that the blood flow is improved if we increase pressure, within reason of course, and is reduced if we increase that peripheral resistance. So there are three main sources of peripheral resistance within the body. The first one is looking at blood viscosity, and this is essentially looking at how thick your blood is. So if I say wave a magic wand and I say bang, all of a sudden your blood is now honey. That would mean that the viscosity or the thickness of your blood is going to be extremely high, and the amount of effort that's going to be required to move and push that now honey in your body is going to be astronomical. The second one is total blood vessel length. And this is a big thing with obesity especially. And what happens there is that the longer the blood vessel is, it means that there is more contact or more resistance between the blood vessel and the blood. Now, granted, we do have a lot of sort of epithelial tissue to minimize that resistance, but it is still there. It is impossible to have a system with zero resistance or zero friction in that regard. And the last one, and the one that we as a physiological system have the most control over, is blood vessel diameter. Now, what we can do here is actually change the amount of peripheral resistance by vasodilation or vasoconstriction. Now, when we are looking at blood pressure, what is important to note is that it is not the exact same everywhere in the body. So when we are looking at our blood pressure, as that blood is leaving the left ventricle through that aortic semilunar valve and out through the aorta to be delivered to the rest of the body, that is when blood pressure is at its absolute highest because it's just left the heart. However, as it continues to get further and further away from the heart, that blood pressure will eventually decrease lower and lower until we basically get to the top of the vena cava. And that is when blood pressure is essentially at its lowest because it's right at the very end where it's about to go back into the pump and resume circulation. So what we do here is that we can look at this systolic pressure. So this is the pressure exerted by our heart when it's in constriction. And we have our diastolic pressure. This is the pressure that is in our arteries during relaxation. Because our heart is not just able to sort of tense the whole time and keep pushing things out. It needs to relax and have those chambers fill. So we're seeing these sort of fluctuations in terms of the systolic pressure and diastolic pressure. This is why when you go to get your blood pressure measured at the doctor's or at a pharmacy, this is why you'll get a readout of two numbers, typically 120 over 80 millimeters of mercury, mmHg. Now, what we can then do is take those two figures and calculate a figure called the pulse pressure. And what this is essentially the difference between your systolic and diastolic. This kind of gives an average of the two. Now, looking further into our blood pressure, we can have a look at our mean arterial pressure. Now, what our mean arterial pressure essentially tells us, this is the average blood pressure that we are able to measure in an individual during one cardiac cycle. So remembering a cardiac cycle is a period in which the heart is in constriction and relaxation. So how we are able to calculate the mean arterial pressure is that we take the diastolic pressure and we add 1/3 of the pulse pressure. Now, it's not so much important that we understand how to calculate this. What I want you to instead focus on is what the mean arterial pressure is actually telling you, because what it tells us is the amount of perfusion that is occurring in our organs. Now, when I say perfusion, what I mean by that is essentially blood flow or blood delivery to particular organs. So when we are calculating our mean arterial pressure, we should be around 65 to 110. And if we start getting values below that, that's when warning bells should be going off, because what that is essentially indicating is that the body is not producing enough pressure to adequately push blood into our tissues to deliver oxygen and remove waste. So what we see here is a lovely graph looking at this fluctuation in our blood pressure. So what we see is when we're at our aorta, we can see there is a huge variation between our systolic and diastolic blood pressure. And we can see sort of our mean arterial pressure in the center here. And as we move further and further away from the heart and those really big arteries like the aorta, that blood pressure will start to decrease, especially when we get to the capillaries. And we're going to be talking about that in a future video. Then, as we eventually keep going, we're going through the venules, through the veins, we're relying heavily on those skeletal muscle pumps, on those valves that are inside of our veins to prevent that backflow of blood, to push the blood back up into the heart and to resume that circulation. Now, we do have three main ways in which our CNS, so our central nervous system, can control our blood pressure. And essentially what is happening here is that we are receiving signals from many different areas in the body, whether it's the heart, whether it's the kidneys, whether it's various baro and mechanoreceptors in our blood vessels. What they are doing is they are constantly measuring our blood pressure and the amount of stretch that is occurring in our blood vessels, or measuring the measurement of various chemicals, things like oxygen, CO2, and pH, to looking at, hey, is our blood flowing at an adequate rate? Do we have an adequate amount of blood pressure that is fulfilling the needs of our body at that time? If it's not fulfilling those needs, i.e. if you suddenly take off at a dead sprint and your body's going to go, oh my God, I'm not delivering enough blood. I need to increase my heart rate. I need to increase blood pressure. I need to get some blood moving around. What will happen here is that a signal will be sent to the cardio-acceleratory center. And this is found within the medulla oblongata. And what that will do is essentially send a signal from the brain to the heart saying, hey, we need to kick it up a notch. We need to increase that heart rate. Okay, so it's going to trigger those sinoatrial node to fire more frequently. And it's also going to trigger the myocardium to constrict more forcefully. So to push more blood out more frequently. So we're running for our life. We're running, we're huffing and puffing. We get around the corner and we go, woo, we're safe. Now what is going to happen is the body is going to go, okay, wow, we are moving a lot of blood. We're moving a lot of nutrients around the body. We are safe now. We are out of danger. We no longer need to have that dial set to sort of 12 out of 10. Let's slow it down. Let's calm it down. And what's going to happen is that the parasympathetic nervous system is going to sort of kick in and it's going to slow down that heart rate. Now, we have spoken about the cardio-acceleratory and cardio-inhibitory center in our first series of videos, but there's a third one here that I wish to add to this, and that is looking at our vasomotor center. And what that is going to do is essentially control where the blood goes. Not only can it control blood delivery to particular parts of the body, but it can also control that vasoconstriction and vasodilation to control your blood pressure. Now, what I mean by this blood routing is that for me right now, I'm sitting here talking to you lovely people. I've just had something to eat about 30 minutes, 40 minutes ago. I'm currently at rest. And what is happening here is that there is going to be an appropriate amount of blood flow moving around the body. My heart rate is at an appropriate rate, probably 50, maybe 60 beats per minute. I have no idea. But the big thing here is that there's going to be a significant degree of blood flow to my stomach, to my intestines, to absorb all of those nutrients that I've recently eaten. Another thing too is that there'll be a degree of blood flow going to my kidneys to filter my blood and produce urine as waste. Now, if I suddenly see a massive tiger sneak up behind me and I go, oh my God, I need to run for my life. It is not important that I am digesting my breakfast. It is not important that I filter my blood and create urine at that time. Why? Because I've got more pressing issues, i.e. the tiger behind me that's about to eat me. So I need to run. And as we can see here, if we look at rest, we've got 5.2 liters of blood moving around the body per minute. Whereas if I'm running for my life, it's 17.5 liters. It's a huge increase. I'm significantly increasing the amount of blood moving around the body because I'm running for my life. Secondly, have a look at the change in blood flow from kidneys and abdominal organs. They basically halved. Again, because it's just not a priority. We do not need to filter our blood and absorb nutrients and minerals that we've gotten from our food. I am running for dear life. Skeletal muscle over here, 1.1 liter per minute, up to 12.5 liters per minute. It's over a 10 times increase, which again makes sense because these bad boys are getting a workout because I am legging it. I'm getting out of there. Now, all of this that I've just described here can be summarized in a nice little flowchart, and that's what essentially we are looking at here. So if I've finished running for my life, I'm huffing and puffing, I've got my heart rate is up, my blood pressure is up, I'm sweating, I'm an absolute mess, but I survived. I escaped the tiger, because apparently in my wonderful metaphor here, I can outrun a tiger. So what is going to happen here is that everything is going to start slowing down because these chemoreceptors are no longer going to be detecting that my blood is going to be very acidic or I've got a lot of CO2 in my system. My muscles are going to be well perfused. They're not going to have as much demand of that blood. And what is going to happen then is that these baroreceptors and chemoreceptors are going to essentially stop signaling to the body or to the medulla oblongata saying, hey, we need to really ramp it up a bit. They're sort of going to say, hey, we're fine. Let's slow it down. They're going to stimulate the cardioinhibitory center. Let's slow down that heart rate. We're going to stimulate the vasomotor center. Let's reduce that vasomotor tone. So let's relax these blood vessels so that we can reduce our blood pressure, reduce our heart rate, and go back to a normal state.